Hello, this is Imad. In this walkthrough, I will take you through the journey of AuroXRay from its core initial idea to the technical architecture and finally into a live demo of how everything fits together. Honestly, I never set out or planned to build such a full-fledged application. It all just started as an experiment, inspired from the paper of distributed multi-label learning on the Apache Spark. The initial idea was simple: build a library that brings together the power of Vika, Deep Learning 4J, and Mulan, which is by the way, it's a phenomenal multi-label classification library. Now the question is, why CheXpert? I had previously worked with the NIH Chest X-ray 14 dataset, but I wanted something more structured with better annotation quality and something that is a bit more complex and more appropriate for a multi-label classification task. That's when I came across the Stanford's CheXpert dataset, which turned out to be perfect fit for what I had in my mind, tying together deep learning 4J, Vika, and Mulan. Also, this entire project is built with Java, which is quite different from the usual approach, as most machine learning or AI based projects these days revolve around the Python. But part of it was also to prove that Java is as powerful for building production grade AI machine learning applications. And again, this wasn't supposed to become a full-fledged application, but as the project evolves and with the release of Spring 3.0 and Angular 17, somehow ended up becoming a comprehensive, full-fledged application. In all of my projects, whether it's a web application or a desktop application, RxJava remains the core component. One of the key benefits of a reactive programming is that it helps you to write concurrent parallel implementations quite conveniently without thinking in terms of executor service, fork join pool, etc. So the RxJS backend is a combination of Spring, RxJava, and now the virtual threads. Virtual threads are basically hyper-threading within the JVM. And now the JVM can run millions of lightweight threads because obviously virtual threads are much more memory efficient than the traditional platform threads because they don't require to have their own dedicated native stack. So this combination, Spring, RxJava, and now the virtual threads, is actually a very powerful combination. It makes your entire application robust, more scalable, and brings the ability to handle large number of concurrent requests. However, when you're using Spring plus RxJava, not talking about the Spring Webflux, there are a couple of things you need to handle. For example, the transaction management and the context propagation. With Webflux, a lot of this comes out of the box. But since I personally prefer to work with RxJava, love to work with RxJava, so I have to handle these two aspects, the transaction management and the context propagation. Let me just hover over this method. As you can see that the Spring transaction management assumes assumes a single threaded flow where the transaction starts, commits, or roll back within the same thread. So when we are building concurrent reactive chains, there may be instances where our DB queries are executed outside the transactional context. Let me explain you with an example. So let me just write transactional public single. Is Spring JP a transaction? Yeah, it's Spring JP a transaction. Patient create patient patient. It's just a dummy example. Return single dot form callable this dot query builder dot save or update patient. Like just an example, just a dummy example. If I use the transaction annotation here, it would work completely fine. The reason is that the subscriber thread is within the transactional context. That's why the transaction annotation would work completely fine. But when we are building concurrent reactive chains, there may be instances where our DB queries are executed outside the transactional context. Just for example, let me just write something dummy here. Completable, completable.form action. It's just a dummy example. So even in this case, let me just modify this bit. Completable dot and then. So even in this example, the transactional annotation would work fine because the subscriber thread is within the transactional context. If I actually switch the context, for example, dot subscribe on spring scheduler dot virtual thread. If I actually switch this context, now this transaction annotation won't work. And our DB query, DB persisting query would be executed outside the transactional context. That's why it's generally not recommended to use the transaction annotation with the reactive implementation. Therefore, I had to write two helper classes, single transaction factory and the completable transaction factory. That ensures our reactive chain still maintain a proper transactional scope. These classes have two methods, execute transaction and execute transaction in read only. I've also open sourced the gist for it. Also, here's the gist for it. Let me just open it. So what it does is you have to implement the transaction synchronization manager. There's a method is actual transaction active. So if the transaction if the transaction is active, you put this entire code block in that if block, and in the else block you continue with this code block. So what it does is, what the completable transaction and the factory and the single transaction factory does is, it first checks whether the transaction is active. If it's not active, if it's active, join with the existing transaction. Otherwise, create a new transaction using the transaction template. That's basically the purpose of the execute transaction in read only. So all our reactive chains, all our reactive code block is wrapped within the execute transaction or the execute transaction in read only. And this ensures that transactional boundaries are maintained within the reactive execution. Meaning, all the operations wrapped inside this block run within the same transactional context. That was all about the Spring transactional management. Now the context propagation. So when we are using Spring JPA auditing, we have two fields, last modified by and the created by. These two fields internally rely on the security context holder. But when we are using Spring plus RxJava, both our controllers and services are running on different threads. So the context is lost. So when we are persisting these values created by last modified by, the security context holder returns the principal object as null because the context is lost. Therefore, you need to implement a context propagation implementation. For example, scheduler context propagation, single context propagation, completable context propagation, etc. etc. The workflow is, you first capture the context before the execution, propagate that context before running the task, execute the task, and then finally perform the cleanup. This context propagation ensures that the context is passed across the RxJava threads. That was all about the transaction management, the context propagation. Now we are going to discuss the workflow explanation, data pre-processing, which were done on the CheXpert dataset, feature extraction, optimizations, which were done on the binary relevance, and then finally showcasing a live demo and explaining how everything works. Also, one more thing, to explain it, let me modify this patient service implementation. So I'm just copying this code line of code and return. That's perfect. Now we are going to invoke this service implementation, this service method on the controller side. So just give me a minute. So I'm just adding some random mapping, create test, public, returning it as single patient response. Perfect. Create test. The service method expects the patient object. So let me just create this request body, patient, right? So return this dot patient service dot create patient and dot map. We are actually transforming that patient object, mapping that patient object to the patient response. This dot mapper helper dot map p map to the patient response. Now to explain this, in this scenario, the transactional annotation would work completely fine because the subscriber thread is within the transactional context. But in our scenario, we want both our controllers and service implementation to be executed on different threads. Therefore, so let me just use the subscribe on spring scheduler dot virtual thread. Now in this case, this transactional annotation won't work because the subscriber thread is outside the transactional context. So if you actually log this method, log this implementation by, for example, system.out is transaction active, and you just use the transactional synchronization manager dot is actual transactional active. When this method is invoked, when you're using the subscribe on, you will find that this would return as false in this from callable block. Why? Because the subscriber thread is not within the transactional context. So this query, this persisting query would be executed outside the transactional context. Now, why the transaction annotation won't work? As I've said it before, because the Spring transaction management is bound to the thread that invokes the method. Spring transaction management assumes a single threaded flow where the transaction starts, commits, or rollback within the same thread that is invoking this service method. It does not automatically propagate the transactional context across the thread boundaries. In our scenario, since the controller and the service logic run on different threads, due to the subscribe on call, the transactional context won't automatically carry over to the new thread. And this persisting query would be executed outside the transactional context. This transaction annotation won't work because the subscriber thread is outside the transactional context. And that's why these classes, the single transaction factory or the completable transaction factory, were created. Let me also mention something which I forgot earlier. Even though I'm using Spring plus RxJava, all my service implementation, all the implementation on the service side is essentially a blocking code. The reactive and the concurrent implementations or concurrent chains are implemented on the controller side. So basically, all the DB queries, business logic, everything happens in a blocking manner. Let me just hover over this method. As you can see that essentially all the business logic on the service side is a blocking code. All the DB queries, business logic, everything happens in a blocking way. But they are wrapped inside the helper methods like execute transaction or execute transaction in read only, which either returns single or completable, either returns the reactive type, either single or completable. So basically all the implementation on the server side is a blocking code, and all the reactive and the concurrent chains are implemented on the controller side. Let me just start this RxJava service application, and I'm also starting the Angular application. ngserve port 4200. So everything is working fine. RabbitMQ, SNS, and PostgreSQL. The Angular application has also been started. Let me just log in. So, let me navigate to the classification and the create classification page. So this is how it goes. First, you select the patient either by the patient's name, date of birth, or via mobile number. For example, Christopher. So first you select the patient. You can also select the patient via mobile number as well. Let me just give you an example. So first you select the country, Australia, and then you just provide a mobile number. Spacing or no spacing doesn't matter. The only thing is required that your number should be validated. Your number should be completely validated with respect to the country. So this is all the dummy data. Then the first step is you select the patient and then you select the data set. Currently only CheXpert, and then pick the relevant findings. Only maximum 4 is allowed, and I believe that's more than enough for the chest X-ray classification. And then you choose whether or not you want a heat map, and finally provide a chest X-ray image, and then finally click on the perform X-ray classification button. So what happens under the hood is that first it performs the validation, upload the chest X-ray image, and then create a new X-ray classification, set the status of the processing. Then on the success, it performs two operations concurrently in the background. Sends a real-time message to the front end via Storm plus RabbitMQ. On the Angular side, I'm using Storm.js plus RxStorm, and then execute the inference chain. Also, we are using the merge array since the order doesn't matter here. Now for the inference part, the request goes to the AuroXRay machine learning service. Once the inference chain is executed, the request goes to the AuroXRay machine learning service. Obviously, we are using exponential backup strategy using RxJava. So the AuroXRay machine learning service first fetches the image, resize the image to 320 by 320 using aspect ratio plus padding approach we will discuss in a bit, and then extract the features. We are using Denston 121 as a pre-trained transferring learning model for extracting the features. Then transform them into a Mulan computable instance because I'm using binary relevance algorithm. And then finally performs the classification based on the selected radiological findings. Whether it succeeds or fails, it pushes the results to AWS SNS. It pushes the payload to AWS SNS. Our main service, which is RxJava service, is a subscriber to the AWS SNS as well. So it subscribed to that SNS topic. Once it receives the payload, updates the DB record for X-ray classification, set the processing status to completed, and sends a real-time message via Storm plus RabbitMQ. If the heat map is true, it concurrently updates the DB records, set the processing status to generating heat map, sends a real-time message via Storm plus RabbitMQ, and then finally executes the heat map chain. On the heat map side, AuroXRay machine learning server generates the heat map using the ScoreCam methodology. Then again, it pushes the result to AWS SNS on both success and failure. Then once the RxJava service receives the payload, updates the DB, and sends a final message to the Angular, which is our front end. And as I mentioned earlier, the biggest benefit of a reactive programming is that it makes the concurrent and parallel flows incredibly convenient to implement. It keeps the code clean, modular, and highly responsive. All of these, sending, receiving payloads, updating DB records, executing inference chain, executing heat map chain, they all are reactive chains. And this is the biggest benefit of a reactive programming. It makes the concurrent implementation not only convenient, but also highly responsive and efficient. Now for the data pre-processing, the original dataset contains 224,316 chest X-ray images across the training, validation, and the test set, representing over a range of more than 60,000 patients. So here's the original dataset distribution for the CheXpert dataset. You can see that the total images of the CheXpert were 224,316 images. The validation set had 234 images and the test set had 668 images. So I broke down the pre-processing into 5 steps. First, removed all the rows, all the instances where all the labels, all the attributes were actually missing. All the labels were actually missing. These rows weren't actually useful for the training. So after filtering them out, the dataset was reduced to 222,568 images. Then the second step was to randomly split the data into 80% for training, 10% for the validation set, which is going to be used for the DL4J multi-layer perceptron classifier for building our model, deep learning model, and the 10% for the testing set. Now, the third step was to handle the missing values and also to resolve the data imbalance for the support devices. So I've treated all the uncertain labels which are represented as -1 as zeros for all the attributes, and then for the only exception was support devices, where I actually treated all of its missing values as zeros to resolve the problem of data imbalance, as you can see that. Now the fourth step was to discard the no finding attribute. I completely discarded the no finding attribute from the dataset. The idea behind the AuroXRay is to classify the findings based on the specific patient symptoms. So no finding label didn't really align with the objective, and it only contained once. You can observe the data imbalance we are going to end up with. So the data set was reduced to 222,507 images. Now, for the CheXpert dataset, on the feature extraction step, we discarded and removed all the 10 images that were not in correct shape or that does not conform to the CheXpert. Here is the example. As you can see that all of these images, all these 10 images were completely removed and discarded on the feature extraction tab. So after all the pre-processing, the final data set shape is the training set had 178,000 images, the test set had 22,246 images, and the validation set had 22,251 images. Moreover, all the previous studies on the CheXpert often just use 5 labels and a very small subset. For the validation, they are using the validation set which had 234 images and the test set has 668 images, which are actually manually annotated. They have treated all the missing uncertain labels as zeros and sometimes treated only the uncertain values as positive. But obviously, when you're treating all this missing values as zeros, you're going to end up with a major problem, and that is a label sparsity, because there's a data imbalance and you would end up with overfitting problem. Now, to avoid that, I treated this problem as a single label binary classification, but basically building a separate model for each label, dynamically removing the instances with missing uncertain labels at the runtime. Here comes the concept of sparse binary relevance. Again, the only exception was support device, where I kept all the missing values, all the missing labels as zeros to help bring the balance in the data set. Now for the image resizing, normalization, and the feature extraction. All the images were resized to 320 by 320 pixels, which is inspired from the original CheXpert paper. I actually did the experiment with different other pre-trained models such as Inception v3, but DenseNet 121 completely outperformed it, including in my past experience with the NIH dataset. So in this project, and generally for me the best approach for resizing image is aspect ratio plus padding approach. So when working with the CNNs, convolutional neural networks, we need to provide a fixed input matrix. Now there are plenty of resizing algorithms such as LenCos, bilinear, bicubic, etc. But generally for CNNs, I have found that this approach, aspect ratio plus padding approach, is actually the best approach. Why? Because generally some algorithms like bicubic and bilinear, etc., they distort the features. However, this approach keeps the spatial relationship of features like edges and texture completely intact. I would say completely intact. The best analogy for explaining this is, for example, I want to resize an image using Photoshop. So the first step is I actually draw a canvas of a fixed size and then drag and drop the particular image into that canvas and fit it. Just fitting it nicely while maintaining the proportions. So that's exactly what this method is, aspect ratio plus padding resize approach. Now, the normalization and feature extraction. Once the images are resized, the next step is feature extraction, and I'm using density 121. But before that, the normalization is quite critical because nearly all the pre-trained models expect a certain input range. There are two main pre-processing steps. One is necessary and the other one is optional, but highly recommended. So the step one is you scale the image matrix. Each pixel value must be scaled to the range of zeros and one by dividing by 255. Let's say you have a pixel value of 128, you divide it by 255 and you normalize it into the range of zeros and ones. This is the most basic form of normalization and it's required for nearly all the pre-trained networks. The step 2, which is quite optional, standardizing using mean and standard deviation. Once you have scaled it to the range of zeros and ones, we normalize it using the mean and standard deviation values, either from the ImageNet values or the calculated directly from the dataset. By the way, I have written the entire script using deep learning 4J to calculate mean and standard deviation values for the entire dataset in parallel actually. And it's a grayscale image, so we are going to have same values for red, green, blue channels for both mean and standard deviation. All these three channels are identical, so you will get the same number for each. When you're not training the model, you're just extracting the features. Normalization alone is completely enough. It's actually more than enough. So for feature extraction, image normalization, which means the step one, normalizing it to the scale of zeros and one, is completely sufficient. Now, the iterative feature extraction. Now the concept of iterative feature extraction. The core objective of this AuroXRay project, of this entire project, was also to extract the features in an iterative subsets to make it more computationally efficient. For example, so for instance, if the training set, like in our case, the training set had 1,78,000 images, and the batch size, like so for example, the batch size were 20,000. I would load first 20,000 images, extract the features from the density 121, append them into a proper ARFF file, and then repeat until all the image features are extracted. This batching approach is actually more computationally efficient and also makes it easier to scale. For example, especially if you're working with multiple GPUs. Finally, once all the batches are processed, the ARFF file, in my case, is to transform into a Molan compatible format because I'm working with the binary relevance and sparse binary relevance. We'll discuss it in a bit. Also, for the post feature extraction, once, even after extracting the features, it helps to apply another round of normalization or standardization on the flattened or extracted features before training a model on top of them. Why? Because the extracted features or extracted feature vectors can have different distributions, skewed ranges, or varying scales. So you can also try without the normalization or standardization, whichever gives you the best result. There's no one size fit for all, but it's a good practice to try and apply the normalization or standardization to an extracted or flattened features. Also, since I'm using Vika Deep Learning 4J, so Vika Deep Learning 4J's design pattern is that the ARFF file should contains only two attributes. One is the file names, original file names, and the second attribute is the corresponding labels. So Vika Deep Learning 4J has a class ImageInstanceIterator. What it does is it transforms the instances into Deep Learning 4J's dataset iterator. So by default, the image instance iterator performed this normalization using the deep learning 4J's image preprocessing scaler, which scales each image pixel values to zeros and ones. Let me show you an implementation. So let me just go over this. Let me just close this DL4J inference classifier, DL4J MLP classifier, image instance iterator. Let me see, just see. Get data set, yeah. So you can see that by default under the hood, the image instance iterator performed this normalization using this deep learning 4J's image preprocessing scaler, which scales each image pixel values to zeros and one. So generally for feature extraction, this sort normalization alone is sufficient enough. Now for the image augmentation. Generally, when we are training a neural network or a convolutional neural network, we often generate augmented images to make sure the model becomes more generalizable and robust. Ultimately, the goal is to enhance the accuracy. These augmentations simulate the real-world variations and help the model avoid overfitting by exposing it to a wider range of data. On this CheXpert dataset, I applied warping, rotation, and scaling to our training set, which is 178,000 instances. So the augmentation strategy was 1:1 ratio. What I mean by this augmentation strategy as 1:1 ratio, meaning for every original image, one augmented version was created, and ultimately the features were extracted from the augmentation dataset as well. So both the original and the augmented features were merged into the final ARFF file. Here's our augmentation dataset. As you can see that here's our actually augmentation dataset. You can observe that. Let me just show you different examples. As you can see that images are randomly warped, rotated, or scaled. Generally, for the convolutional neural network, real-time augmentation is used. So these augmentations are applied before the batch is fed into the network. Here on every batch, for example, on a convolutional neural network, so augmentations are a transformation. These augmentations or transformations are applied before the batch is fed into the network. So here on every batch, for example, if the batch size is 64, it randomly applies the transformations such as warping, rotation, scaling, etc., on each batch. So even if you train for 10 epochs, your model might never see the exact same image twice. So that's, you can call it as a real-time augmentation. So on every batch, for example, a batch size 64 or 32, it randomly applies these transformation on each batch. So essentially, even if you train for 5, 10 epochs, so more number of epochs, your model might never see the exact same image twice. In this project, since I'm extracting the features beforehand and then training the model, that's why the static 1:1 augmentation strategy was used. And it does simulate the real world variability effectively and also enhances the model accuracy. So the static 1:1 augmentation provide a necessary variability in the image representation. And obviously, without adding any computational overhead during the training, because the features are extracted beforehand and our final ARFF file has both the training features and the augmented features. One more thing which you can observe, that these transformations applied preserves the semantic structure, which is actually very important, super important in medical imaging. What I mean by the semantic structure is that the organs like lungs, hearts, ribs, anatomically remains realistic. They aren't distorted. If the augmentations distort or misrepresents the feature, it becomes medically meaningless. So the ultimate goal was to simulate the real world imaging variations without introducing unrealistic distortions or artificial noise, and that is super important in medical imaging. And thus our model become more generalizable and more robust and ultimately enhancing the model accuracy. Now the binary relevance and the sparse binary relevance. Binary relevance is a multi-label classification algorithm. By the way, if it weren't for a multi-label library like a Mulan, which is built on the top of Vika, I wouldn't have gained such a deep understanding or kind of proficiency with the multi-label classification algorithms. So a big shout out to all those who have developed and contributed to this project. Binary relevance falls under the category of problem transformation approach. So what it does is that instead of trying to learn all the labels at once, binary relevance transforms the multi-label problem into a multiple independent binary classification task. You can just see this example. So binary relevance transforms the multi-label into a multiple independent single label classification. Essentially, we are building a separate model for each label. Each label is treated as a separate binary classification task. And so this allows us to apply all sorts of single label classifiers like support vector machine, random forest, Vika deep learning 4Js, DL4J MLP classifier, and all the lazy learners, etc. So for example, in our case of CheXpert, a single chest X-ray image can be associated with multiple findings, and it's pretty much common with all sorts of X-rays. So for example, a single chest X-ray image can be associated with consolidation, pneumonia, atelectasis, etc. etc. In the earlier part, we discussed the problem of label sparsity, where one approach on this CheXpert dataset is to treat all the missing values for that specific label attribute as zeros, like fill it with zeros. But that introduces a serious imbalance and overfitting problem. The model becomes biased towards predicting the zeros, which means the absence of all these radiological findings and pathologies, simply because zeros dominate the dataset. And that's where the concept of sparse binary relevance comes in. So during the transformation step for each label, with respect to each label, we remove all those instances where that label attribute is missing and then train and build our model. For example, let's take an example of consolidation. So consolidation has like the more than 1,76,000 instances for the consolidation label attribute is missing. So on the fly, during that label iteration, we remove all these instances with missing label attribute on the fly and then train our model rather than treating all these missing label attributes as zeros. So essentially, this is what sparse binary relevance is. We're on the transformation step for each label iteration, we remove all the instances where that specific label is missing and then build and train our model. Let me just search for the Mulan's GitHub repo, and we are going to discuss the problems with the original Mulan implementation and the optimization which I had made for the binary relevance. So let me just navigate to the repo, Mulan. source transformation. I suppose there will be binary relevance transformation class and the classifier transformation binary relevance. Now in Mulan's design pattern, this binary relevance transformation class stores the entire data set and it's a part of a serialized model. Like if you navigate to this class, you can see that it stores the entire training data set and it's become the part of the serialized model. Now that's a major problem. For example, in my case, the final model size is around 45 MB. But if I serialized it with the entire training data, which is completely unnecessary, not even needed, it would be like approximately the final model size would become like approximately 4 gigs. So this is a main class for the binary relevance, which does all the transformation, inference, etc. etc. So first step was to split this class into two different classes. Binary relevance transformation, which is used only for the training purpose. And it's not a part of a it's not the part of a serialized model. And then the second class was binary relevance inference, which is used only for the inference. So this class has two important implementations for the transformation, the shell binary and the shell numeric. And there are two methods, which is this one is for the inference, so it becomes the part of our binary relevance inference class. This is a method for the transformation, so it becomes a part of a binary relevance transformation class, which is only used for the training step. The core purpose of the binary relevance inference is just to store the attribute structure, not the entire data set itself. So I just store only the first two instances to particularly store the attribute structure as a part of the serialized model, not the entire training data set itself. There is no need to serialize the complete data, and that was a necessary optimization, which essentially I would say drastically reduced the model size and obviously avoid memory issues using the deployment. Just imagine it would require at least 5 gigs of memory initially for running the AuroXRay machine learning server and loading the model into the memory. So this approach drastically reduces the model size because it's completely unnecessary to store the entire training data set itself. Basically, the first step for the binary relevance transformation is to remove all the original attributes and replaces them with a single label attribute. For if it's nominal data, so we have binary relevance label where we actually named it as binary relevance label. If it's a numeric data, we can name it as single target regressor label. So this allows us to apply all the classifiers like random forest, support vector machine, DL4JMLP, etc. etc. So basically the first step is to remove all the original label attributes and replace them with a single target attribute. Let me just navigate to the PowerPoint. So here's an example. So when we invoke this shell binary or shell numeric implementation on the constructor, we remove all the multi-label attributes and replaces them with a single placeholder attribute, binary relevance label or single target regressor label if it's a numeric data. And then for each label, we assign values to the new class attribute for each instance. Like that's the first step. When the shell binary is invoked, it just replaces all the multi-label attributes and replaces them with a single placeholder attribute. Assume we have a data set with three labels, label 1, label 2 and the label 3. So the step 1 is when we invoke this shell binary, what it does, it removes all the multi-label attributes and replaces them, all these multi-label attributes, and replaces them with a single placeholder attribute. If the label attribute is nominal, so it would be named as binary relevance label. Now it does not have the values for the label attribute yet for each instance. The dataset is ready, but we need to assign value on each label iteration. So for each label, we need to assign the original values. Original values for that instance based on the label, specific label that we are training on. So for example, if we are training on the label 1, so we have to assign the original values of the label 1 with respect to each instance. And this is how it looks like. Just give me, yeah, this is how it looks like. So each time we assign the class attribute original values to each instance for the label which we are training on, and this allows us to train a separate classifier for each label. However, this current implementation, and this is a main implementation for the transformation, that this is a main implementation which does this all sort of transformation. However, this current implementation for the transform instances isn't fully optimized. And when you're working with extracted or flattened features, especially when the features are rounded to 6 decimals and then there are more than 1,000 attributes with a very large number of instances, so this implementation can lead to a very high memory footprint on training. So the question is, why does this approach leads to a high memory footprint? Let's break it down by step. So the step 1 is, first, it creates a new data set using this code block new instance, this shell binary. So it creates a new data set by copying either the shell binary or the shell numeric. So this means the shell copy instances object now contains a full copy of instances, basically cloning it. Basically, it's cloning it, an unnecessary memory consumption. So this shell copy not only contains the structure, but the entire data set as well. Once this shell copy is created, then it modifies the last attribute, which is a placeholder attribute. It would be binary relevance label or single target regressor label attribute. So it's a placeholder attribute, modifies the placeholder attribute with the original values with respect to that label which we are training on. So what does this code block does? It just updates the last column, which is a placeholder attribute. First, we are cloning the shell binary or shell numeric again, and then we are updating the last column, which is a placeholder attribute or the class attribute with the original values for each instance on each label iteration. Essentially, an unnecessary instance references, and obviously it would have a high memory footprint. Now the question is, what's the optimizations that were needed to be made? So the step 1 is, instead of copying an entire data set, the approach is you start with an empty instances object. In shell copy equals to new instances, this dot shell binary, pass the second argument as 0, capacity as 0. So what does this does? It copies only the structure, not the instances object. We are not cloning the instances object. We are just copying the structure. So basically, no instances, only it copies the structure. And then the second step is we build the data set incrementally. So instead of cloning and then updating the last label values of the last placeholder attribute, we create a new instance from the scratch using the dense instance class. So each instance is directly added to the shell copy without modifying a pre-existing data set. It only creates necessary instances rather than first cloning the entire data set and then updating the label values. So the summary is, first, we refactor the logic entire binary relevance transformation class into two different classes, binary relevance transformation and the binary relevance inference, which is only used for the inference. The purpose of binary relevance inference is to store the attribute, the structure for the instances object, not the entire data set itself. We just store the first two instances to particularly store the attribute structure as a part of a serialized model, not the entire training data set, thus obviously reducing the model size. Then we optimize this transform instances method. So instead of cloning the data again and updating the last column, we created new instances we create a new instance object from the scratch using the dense instance, and basically creating new instances directly without modifying a pre-existing dataset or without modifying a copied dataset avoids unnecessary instance duplication and much more memory efficient for the large datasets. So this entire implementation has been rewritten from the scratch, both the binary relevance transformation and the binary relevance class, with a focus on performance, optimization, and clean structure. Also added the support for parallelizing the binary relevance implementation. You can use the executor service here, basically creating models for each label in parallel, but this would only be effective if you have enough memory and you aren't working with the classifiers which already supports parallelization, such as random forest. And obviously with deep learning 4J there is no need for parallelization, and obviously we are going to use the GPUs for the training. So that was all about the binary relevance and the sparse binary relevance. So that wraps up the part 1 of the AuroXRay walkthrough, where we focused mostly on the building block. We also covered the backend stack, Spring plus RxJava, explored and discussed the transactional context propagation, image preprocessing, the aspect ratio plus padding approach for resizing. We also discussed the feature extraction, data preprocessing for the CheXpert, normalization, and the optimizations which were implemented to improve the binary relevance algorithm. And this was my first time recording, so yes, few audio parts may sound overcompressed or awkward, but thanks for bearing it with me. In the part 2, we will move into full demonstration of the AuroXRay application, and we'll also discuss the model evaluation, including the metrics from a multi-label perspective, such as subset accuracy, ranking loss, coverage, average precision, etc. and more. So see you in the part 2.